All right, so my name is Ben Chodroff. I'm the Chief Technology Officer at CloudOne. I've been using Python poorly since 2006, so quite some time. I'll jump on the bandwagon. My favorite data structure is a dictionary, but anyone that works reliably is also a very good data structure. So today we're going to be talking a little bit about how does Internet of Things work, and to relate it to the Python group that we have here at IndyPy, I thought we'd talk about a project I've been working on over about the last year, where I've been automating my fish tank with IoT sensors and being able to allow me to automate all the maintenance around my fish tank. So first question I have for all of you, who here has bought a Raspberry Pi? Raise of hands. That is a lot of hands. Now, keep those hands raised, keep those hands raised. Who has bought a Raspberry Pi and has found a use for it yet? Okay, only a few hands went down. So this is where I found a lot of people in talking. We all seem to, in many cases, have bought a Raspberry Pi and maybe haven't found a use for it, or maybe even been intimidated to put it to use to an actual application outside of just running Linux. And I want to show what you could do with this. And the Internet of Things doesn't have to be overly complicated or very difficult. It can be just a thing. It doesn't even have to be plural. And that's really what I've done here with my aquarium. So before we get into all the technical gorp of how you do it, I like aquariums. They're really pretty. There are fish inside there, so you got responsibility, and there's this maintenance aspect to it to make sure it all works. But when it all comes together, it's pretty. And that's why I wanted to achieve this. I was struggling with my own aquarium. My wife, when I met her, actually at the time we were only girlfriend and boyfriend, she was at a carnival and through typical fashion, throwing the ball, the ping pong ball, and she won a goldfish. Thousands of dollars later, I am now with this. But yeah, there was she got it in. Yeah. So this is where it's ended up. I've taken the hobby to different extremes and combined different hobbies together. A love of computers with a love of now aquariums and automation. But today what we're going to do is not teach you necessarily how to build this exactly, nor teach you everything there is to know about IoT, nor teach you everything there is to know about Python, but sort of a high-level cursory overview of all those subjects to be able to say you'll have some comfort around taking potentially the Raspberry Pi you already own, or encourage you to go buy one and go solve any type of challenge that you want. That's what the goal is here. So with that, this is version 2. We won't talk about version 1. It didn't work. So why did I even get into this to begin with? Well, there was the love of the aquarium, but realistically, I did have a pretty burning scenario, which was I left the water on while doing a water change, and it ended up starting to flood my basement. So I had, a cause to go and solve. There were ways to solve this, of course, with using a timer, I suppose, and just reminding myself, go turn off the water because you shouldn't leave it running. But no, let's go over-engineer a solution. So what can we do with this? Well, we could do everything. We could go and collect all the data points. We could get everything, the pH, the temperature, the flows, the levels, the state of the lights, topping it off, removing different types of water and photosynthesis, and how do I dose? I just started going crazy with what it could be. I really wanted to reduce the amount of time I spent maintaining the aquarium. There's a lot of time, if you do an aquarium right, to making sure that you have the pH balance, because the aquarium has very sensitive life in it that can't tolerate big swings in what the pH of the water is. And as well, I like doing freshwater aquariums. And this is particularly important because with freshwater, you have to encourage growth through a couple mechanisms. One is CO2. You need to be able to give carbon to the life to be able to grow the plants. But you also need a number of fertilizers, potassium and phosphates and iron and all sorts of other ingredients to be able to create photosynthesis. And of course, light. Once you combine all these elements, eventually you also have to cycle the water, because you don't want to have an unbalanced aquarium where you have too much of one thing. Otherwise, you have your enemy, algae. And that is the constant enemy. It's balancing happy aquarium critters with happy plant growth with no algae. And if you can do all three, well, you've mastered it. And that's been the challenge. It's very difficult to achieve balance in about 65 gallons. The Earth has millions, billions, and billions of gallons, and it's over eons well, we've got what we have today, and it does it very incredibly well. When you try to scale that down to a small aquarium, it becomes very challenging. I also wanted to get alerts, so inevitably something's going to go wrong, just like in my case where I started flooding my basement. So I needed to get alerts around the maintenance, like CO2, when do I change out the filters, how do I let myself know if I'm about to go flood my basement? That would be nice to know. Or the reverse case, if perhaps the level drops significantly. Maybe I'm not topping the water off, but something happened in the aquarium where a lot of water is gushing out from another source, and that's also equally bad. I want to know if it gets too low. Temperature and pH, etc. So a lot of things to go consider. So I've gone through a very iterative process to build this out. This is my aquarium. It did not start here. In fact, when I first started out, it was crowded with algae, and I had unfortunate deaths in the family. So it wasn't going very well before I tried to tackle this. And through this process, I not only have made something that I find visually appealing, but I think all the critters would agree it's a much better system now. So how did I get to that? Well, before we get into that, I always like to start with the demo rather than after all the fact, because it's so much more interesting to see what it all came together as. This is actually a live dashboard that's on the internet. You can go to the same URL, it's in the presentation. And I'm using a Freeboard, which is a free dashboard creating system which pulls information from a controller, my Raspberry Pi, and it's getting pushed information over an IoT messaging framework called MQTT. And this is allowing me to see real information about how my aquarium is doing 24/7. So with this information, I can keep track of my pH, and I can see information about how it's doing over time, and it's keeping track here. My water level in centimeters, the temperature of the aquarium, and the flow. So it allows me to see, oh, it dropped down here a little bit. I wonder what's happening. Perhaps one of my inlets is being blocked by some media, and I got to go change out a filter. It also allows me to see which devices are running. So I've got different pumps running to be able to control what type of fertilizer and different states of my aquarium. And the devices to do maintenance, such as water top-off, which I do every morning to make sure that it stays at a frequent level, but also weekly I do a removal. That was a real pain before. Take about an hour of my weekend to go and haul a bunch of water, pour it into the aquarium, and take some water out. It's a real challenge, and if you don't do it precisely, the whole balance gets ruined. And of course, my favorite piece is live video. I love the fact that I can see my aquarium. This is live. This is over YouTube. YouTube has a great service we'll talk about in the presentation, where you can take your Raspberry Pi and the embedded camera module that you can buy for the Raspberry Pi, and you can actually stream 1080p video over the internet. I kid you not, I was in China, and through a VPN service to get past the Great Firewall of China, I was able to watch 1080p of my aquarium and perform a remote water change procedure from China. So it's pretty incredible what you can do. I never imagined that this would be the end result. It's been an interesting process, and I thought through this session today we can teach you guys how you can get started in doing these type of challenges. And I'll even start to talk about where I hope it to go in the future around analytics and doing IR detection of the photosynthesis levels of my plants, which is kind of a future state. So with that as a backdrop, let's get into how did that happen. It all starts with the Raspberry Pi, and again, you don't have to choose the Raspberry Pi. I like the Raspberry Pi for a number of reasons. I don't like the Raspberry Pi for a good number of reasons too. The reasons I do like it is it's cheap. You can't argue with the $30 cost point. For that cost, there aren't too many other competitors that I find is easy to work with and provides full Linux and also has a great community of developers and makers all revolving around it. So for that reason alone, I highly recommend it. The Raspberry Pi 2 has a lot more power and capabilities. I started with the Raspberry Pi 1. It's a little underperforming for some of the more complicated tasks, but it's perfectly suited for quite a few of them. You can run Python. It's got built into it, well, not built in, but you can go and download Linux for it, and you can get, it comes pretty easily to get Debian Linux, so whatever version of Python's there, you can easily run. The camera integration is excellent. For $25, that picture is pretty incredible. I think everyone would agree that over the internet, that's what type of live streaming you can achieve. And it's fairly easy to IoT enable. In fact, if you were watching the news, they launched a new Raspberry Pi 3, which now comes built in with this. But for the 2, you can buy for $10 a Wi-Fi dongle, or in my case, I ended up using the Cat 5 cable just for reliability. So the first thing I recommend anyone who's going to connect hardware to a Raspberry Pi is to know what the pinout is. So this is a great picture you can get on Google. I have it in the slides. If you don't have it, it usually comes packaged with the Raspberry Pi. You need to know and understand what this picture is telling you. It's telling you what each of the 40 pins on the Raspberry Pi 2 is doing. And it's literally saying this pin is, in this case, pin 01 is 3.3 volts. That's the data line for voltage to be able to get voltage to be able to power any of your devices. Then you've got a number of GPIO. All the Raspberry Pi pins that are GPIO are digital only. So when you start working with these type of digital devices, like embedded sensors and such, you have to realize, is it a digital device or is it an analog device? The Raspberry Pi, one of its weaknesses, not very good at analog. In fact, no analog to digital converter. So if you have an analog device like temperature, you need to think, well, how am I going to get temperature from an analog sensor into a digital Raspberry Pi? We'll talk about that a little later. What I end up doing is I take all these different pins and I start mapping them to what I want to do. And this is probably the most tedious process because you have to start thinking ahead about, okay, what does this pin do? So for example, GPIO2 is pin number 3, and I list it down here. And I say, I'm going to connect that up to this particular device, Relay 1. And Relay 1 is going to control my water change pump. So you start to build out this mapping, and you're going to want to refer back to this as you start to lay out your circuit. But this is a really important step. So really, first thing, start to think of what you're connecting and how it's going to map back to the Raspberry Pi. So what did I connect? Well, you saw that I had all those dosing pumps. And so in order to control the pumps, they're just simply on and off. If I turn it on for a little bit of chemical comes out. If I turn it on for a long period of time, more chemicals come out. So by using an 8-channel relay, which I bought on Amazon for $10, you can control either DC devices, like my devices are, 12 volts, and they can go up to 10 amps, so you can control a pretty significant device. Or if you're feeling ambitious, you can connect it up to AC voltage and also control up to 250 volts at 10 amps. So realistically, anything you want to control. For a while, I did have it connected up to an electrical outlet so I could turn things on and off. But for my purposes, I moved exclusively to DC for safety's sake. These are really easy to hook up. I thought there'd be like all sorts of circuitry that it would be involved to connect this particular device up. If you look down here, and I'm pointing right now to these pins, there are 8 pins which connect to 8 GPIO connectors, and then there are 2 additional pins. One of those pins is power, and the other pin is ground. So if we flip back to this slide, as long as you power it via DC power, and you connect it up to ground, and you figure out which of the other 8 pins go to one of these GPIOs, congratulations, you've just now controlled a device. That's how easy it is. There's no resistors, there's no capacitors, there's no transistors, you didn't have to solve any of that. You just connect A to B, and you now have control of devices from your Raspberry Pi. So how do you do that? You can use the Python GPIO library, which allows you to set the pins to high and low, and just like it sounds, you turn them on and off. It's that simple. So here's some sample code. I like simple examples that I can wrap my head around. So on the left-hand side, I've got English, and on the right-hand side, I've got Python. This is as plain and simple as it gets, and it makes it really simple. What we're doing is we're importing in the Raspberry Pi GPIO library. We got a question. Is there any way to zoom the code? Maybe. Let me see. No. But I will have it in the SlideShare. It's on slideshare.com. And I also will provide the GitHub library at the very end so you can even see the sample code I have out there. But I'll try to call it out. Great question. And feel free to ask questions as I go through this. So just the English alone, we're importing in this GPIO library. We're importing in time so that we can keep track of the commands of when we're executing. So if I want to turn on a pump, for example, for 1 second, I need to know how long a second is. Then I'm going into what's called BCM mode. This allows me to map the pins, like I was saying, 1, 2, 3, 4, 5, 6, to two actual numbers. So that way I don't have to remember it's GPIO 17. Well, that's just pin 12. So BCM mode for me was the easiest to remember, and you can go figure it out. This pin list is an array of all my pins that I'm using. So if I go back to the couple slides before and I look at my list of mappings of pins to actual GPIO, this is just showing me which of them are connected to my relays. For each pin in the list, I'm going to set the pin to output mode, meaning I'm going to send voltage out that pin. You can either put a pin into output mode or you can put it into input mode. Those are your choices. So for this, I'm sending out voltage, and the voltage is either going to be high or low. So if it's high, it's going to be 3.3 volts. If it's low, it's going to be close to 0 volts. And the idea is that that is how we tell the device turn on or off. We're taking a very small amount of voltage, and we're not sending it to the device. We're only sending it to the relay. The relay then controls a larger amount of voltage. In my case, 12 volts, but you could go up to 258 AC. So we initialize the pins to high. Now this is counterintuitive to me, but high in this case means turn the device off to this particular relay. And this allows me to say, by default, don't turn on any of the pumps. So I've just turned on the device, but I have not actually sent any voltage, or I've sent voltage, which means keep the device off. And then this last for loop, I'm looping through the list again. In this case, I'm again setting it setting it to low, my apologies. And that means we're going to turn the device on. I'm going to wait a second, and then I'm going to turn it off. So all I would hear in this case is click, 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 click. And that's going to let me know, okay, I've just looped through all the arrays and I've relays, and I've made sure that every single device can work. Pretty simple.
So question on setting them to high.
Yes.
High is off. Does that mean that the relay in its default unpowered state turns on all of the pumps and things?
Great question. So the question was, what is the default state of the relay when I first power on this Raspberry Pi? And that's a really important question to ask yourself, because if you ever reboot your Raspberry Pi, are all my devices going to turn on? That could be really bad, especially if they're controlling all the chemicals and all the dosing. Or the water state, start filling up the aquarium until it gets into the command. In this particular case, the answer is no, they default to off. But it is incredibly important to ask that question, because you want to make sure you know definitively that if you reboot the Pi, things aren't going to start turning on without your knowledge. What's interesting, though, is it's technically not even off. I've noticed it's kind of in a float state. Even worse. If you turn it on, you'll notice the LEDs on the relay are kind of half lit, half not lit. And luckily, it means that they're not turning on, but be careful. For certain devices, you might get something unexpected. So always best to understand, how do my pins initialize before I initialize them? And you want to make sure you test that before hooking up any workload. Great question. Any questions? Yeah, yes.
Yeah, does that depend then on whether you're using like a normally open or normally closed relay, or are they just double closed?
It depends on the relay type, and I believe even on this relay that I purchased, I haven't played with it, but there is a jumper setting here, and the documentation, as best as I can tell, is all written in Chinese. I didn't even look, but it's quite possible that I could have changed the default relay state to be normally opened. There's also 3 terminals per relay, and depending on how you wire it up, you want to provide power to one of those terminals, and then the other 2 are a switch. And depending on the state of that relay, you'll get different behavior. Trial and error. There's not, especially if you're playing with DC voltage, it's a lot of fun to play with in an afternoon to figure out how to do it. But the documentation was not provided with the device. It was $10 and you got the device.
Well, it's a really common pattern, because what you're doing is you're switching the low side.
Yep.
So the high side of the relay is up. So when you're on, they're essentially the same potential, and it doesn't energize it. When you ground it, and the reason when you ground it, it turns it on, so now it has a path. You can always sink more current on the ground side.
Yep.
So instead of high side switching, you do low side switching. And so it's really common. You'll see this inversion everywhere. And the reason you're seeing your ports flutter is they go into a high and even state at the beginning.
Yep.
Because they're like, I don't know what you want me to do, and it's like, position do no harm. So you're kind of seeing, I don't know whether I should be involved in this or not, on the indicator LEDs, but really it's require a lot of current.
And this is a good opportunity to remind everybody, I am not an expert, and you should never use this code in production until you test it with an electrical engineer. Moving on. This was the hardest sensor of all to wire up. This one does require a little bit of circuit knowledge, but I'm going to walk you through it. It wasn't so bad. So remember those statements earlier about analog devices don't work with Raspberry Pi? That's not true. It's more that it's more difficult to make it work with the Raspberry Pi. You need an intermediary chip to be able to do analog to digital conversion. And so for that, the tried and true method is to use an MCP 3008. What it does is it basically allows you to read off an analog channel voltage and convert it back into a digital signal, a number of 10 bits. So from 0 to 1024. And with that number, you can then convert that particular number into any number of data that you want to use. So for my purposes, I want to know what are the number of centimeters of water in my tank. So this device is a little pricey, but you can get it from adafruit.com for the low, low price of $60. You want to make sure you buy the one with the jacket. They do sell one without the jacket, which is less, and you're like, sweet, I can get a cheap device and it'll save me some money. No. Make sure you get the one with the jacket because they don't tell it on the website, but you get a built-in voltage divider out of the box. So unless you want to learn how to make a voltage divider and make sure you do it correctly, just get the one with the jacket and you'll make your life a little easier. Not that hard, but a little easier. What you get from this device is 3 wires. You get a red wire, which goes to 3.3 volts, a black wire, which should go to ground, and a white wire. The white wire goes to your analog to digital converter. And this is a voltage coming out of it that'll be from 0 to 3.3 volts, corresponding to the level of the tank. But what does 1.7 volts mean? Well, it doesn't know. You have to tell it. So what you need to do is create a calibration points. And you don't have to overthink it. Just 2 points and you'll get a slope of a line and you'll be good to go. I'll talk through that in the next slide. This is the hardest sensor though because it has to go into an analog to digital converter. So what you're going to have to do is map all these pins 16, 15, 14, 13, 12, 11, and 9 back to pins on the Raspberry Pi. There are really great guides. This one in particular on Adafruit did a great job. Great sample code. I'm not going to take all the time to go through all the details, but basically you've got a voltage, which is 3.3 volts. You've got some ground symbols, and then the 3 pins to read off the data are your clock, your digital out, and your digital in. And we take what's called a bit banging approach. Again, I'm not going to get too deep into what bit banging is, but if you follow the guide, you'll be an expert at it, and they provide really good sample code. What it allows you to do is get a number back, and that's all you cared about. You just need to know what's the level in there. It isn't very accurate. I was able to get about an accuracy of 0.5 centimeters, and it took a lot of work. And the reason it took so much work is because it's very sensitive to voltage. If, for whatever reason, your power supply for your Raspberry Pi is not sufficient quality, you'll see wide swings in the measurements. So it's really important to make sure you have a high-quality power supply so that as you're providing voltage to your sensors and your Raspberry Pi, they don't fluctuate in value. And another thing that I had to do was measure a known resistor. So I have the water sensor connected to channel 0. Connected to channel 1 is a resistor that gets 3.3 volts ran through a resistor. And this allows me to measure a known non-changing value. Really important because it provides a good safety alarm to say if that value changes significantly, and by significant I mean like any bit at all, something's wrong. Something terribly wrong has gone on in that circuit. Something about the voltage or reading that number is bad. Throw that calculation out. Again, you're probably not going to be able to read that code, but it'll be in the GitHub repository, and I'll try to call out the English. It's very similar. We're importing our time. We're setting up our BCM pins. We have a function called read ADC, and I have shamelessly stolen this from Adafruit, so apologies to them. But what you're doing is you're sending in what channel to read, which is a number from 0 to 7. It can measure up to 7 analog or 8 analog signals. And you've got a clock pin, MOSI and MISO pin, and your CS pin. What we're doing is we're controlling the clock on and off to be able to read in and out data to this device. And I'm not going to get into the details of how this works, but what you get out of it is a number, and that's the most important part. We take that 10-bit number to determine the level using calibration. So how do you calibrate a sensor? Well, for this case, it's pretty simple. You don't have to get into regression models here. You just say, I need a high point and I need a low point, and I plot a line. That's it. So if you remember your old math days, you need to be able to calculate the slope and the intercept. Finally, we have a use for it in the real world. Now, you can do this really simply without having to use NumPy, but if you want to know how to use NumPy, because you wanted to go play with NumPy, you can use NumPy 2 to calculate the slope of a line. It can do that too. So in this case, we calculate the slope and we find the y-intercept, and that allows us to take readings from this sensor and turn it back into centimeters of water in the tank. Now, again, as I was saying before, to avoid false readings, best to also have a fixed resistor connected to an additional channel. And I did it such that my code says here, the level is going to be the slope of the line plus the intercept. And if that reference median exceeds 3, meaning that within a margin of error of 99.99% certainty, just throw that measurement out. I don't even care. It's probably inaccurate. And that's helped weed out some weird floating numbers that I've occasionally seen just because the Raspberry Pi is not the most perfect solution. I also use a median function. I was finding that if I just took a reading, depending on slight minutia of like voltages and such, it may swing a little bit. But if I took about, and I think I have a 500 here, but realistically I think I got it down to 100. If I take 100 measurements, and these measurements take a couple milliseconds to run, if I take 100 of them and I just look at the median, it's good. So it gets rid of any false positives on the extremes and just says, look at the middle, and that's usually the right answer. Now the other sensors are so much simpler to do. They're as easy as really the relays. I got these from Atlas Scientific. They're not the cheapest, but they're worth every penny, especially if you're not interested in building your own circuits. In these cases, I purchased a pH sensor. The circuit red one down here is the pH. I also got this blue one that's pretty and has little flashing lights. That is the flow meter sensor. And I also have their digital temperature probe because although it's really easy to use a thermistor, I like the fact that it was all serial interface and made it really simple to interface to. Two other devices I recommend are the power isolation module and their serial expander. When you start mixing electronics and water, who knew? They don't mix. So it starts to get important about avoiding ground loops and other types of electrical noise that get introduced. Like, for example, your filters turning on and off or your LED lights turning on and off. You don't think about it, but every time that happens, there's induction current and there's all sorts of weird noise that just goes through the water. This power isolation module separates all the electrical noise of that equipment from your sensors. And so for things like pH probes, it's vitally important or you won't get good readings. They'll fluctuate all over the place as noise happens. So it's not cheap, $36, but it works beautifully, and you don't have to worry too much about how to set it up. They've got great documentation on their website, specifically for the Raspberry Pi 2. The serial expander really helps as well. For $11, it allows you to connect not 1, not 2, not 3, but 4 serial devices to your Raspberry Pi, which normally can only work with 1. So this really is a very cost-effective solution to being able to connect multiple serial devices up. And again, if you don't want to have to build your own circuits, it makes it really simple. One thing I did do that was cheaper is I did not use the Atlas Scientific flow meters. I used a cheaper flow meter from Adafruit. Theirs was only $9. Atlas Scientific had really nice industrial ones that were like $150. The fish will just have to suffer. I provided the links to the data sheets, but I highly recommend going out to Atlas Scientific. They got lots of resources out here. These are some of the wiring diagrams. So down here is the pH. It's not that hard to connect up. As you can see, you've got one of these pins goes to ground, which is pretty simple. And then you've got a receiving pin and a transmission pin. And each of these goes to the serial expander. Two wires. You literally connect A to B. Just make sure that your receiver goes to transmitter and your transmitter goes to receiver. You want to make sure they're talking together. And then this circuit that they provide you connects directly to the probe. So they provide a BMC connector. That's where your probe connects in. And you're just simply saying, connect my probe wires to the circuit. And you just pop it in and it just works. So it removes the whole electrical engineering factor unless you really want to build it yourself. This is what the picture looks like when you start connecting all the sensors together, and you want to also include the power isolation. So it becomes a little bit of a spaghetti wire scenario, but it's pretty straightforward. There's, again, not much circuit knowledge here. As long as you can read the documentation and connect A to B, you'll figure it out. And I admittedly connected it up wrong for a period of time, and it didn't fry it out. So they did a pretty good job at making it pretty simple for even students to learn. So once you have all that wired up, how to use Python? And again, the code's in GitHub, but we're opening up a serial connection. So we've gone through analog devices, we've gone through digital devices, now we're talking about serial devices. Serial works very similar to the digital, but what we're doing is we've got a device on Linux called dev tty ama 0. And we open up a connection. I opened it up at 9600 kilobits per second, but I believe it goes up much faster if you need to do it much faster. That serial expander device, that yellow device that allows you to have 4 serial devices, it works based on 2 pins. And you can create a mapping file that says, okay, if pin 0 and pin 1 are both 0, that means it's device 1. And if 0, 1, then it's device 2. If it's 1, 0, it's device 3. And for my case, I didn't have a device 4. What I'm doing here is I'm using the text I/O wrapper and an I/O buffer to start reading messages off the serial connection. So if you look at the code over here, this text I/O wrapper, all it's looking for is this new line character. When it sees a new line character, it's going to grab that line off the serial and say, I got a line here. What do you want to do with it? So what I end up doing is just looping through all the devices. I'm just saying, okay, for device 0, go read in a few lines to kind of clear out any garbage that might exist on the line, then assume that next line is good to go, and then attempt to read in those variables, and it just reads out text. And from there, in the case of the flow sensor, it's going to put out the current flow rate as well as the total amount that's flowed through the pipe. And I split that variable up, and if I happen to try and accept fail, then I just say, well, I tried, and return unknown if I couldn't get it. And it's very similar for the pH. It's just going to put out the pH every second. I just keep grabbing it and parse it. Not too hard. Pretty easy.
And this started from your wife's ping pong ball? Like,
yeah, to bring it back full circle, all because my wife threw a ping pong ball into it. So like butterfly effect here. It's pretty crazy. But it's grown out of control for sure. The video was a really nice bonus, not necessarily IoT. I might be able to do more of this later, but I thought this was really cool, and there wasn't much documentation out online on how to achieve what I did with the streaming video, so I wanted to share the knowledge here. This took me a lot of work. It turns out the real secret sauce to this is you need a specially compiled thank you, Microsoft. You need a specially compiled FFmpeg library for the ARM processor on the Raspberry Pi. Do not use the one that's built into Debian, which they generically compile for probably x86. If you use theirs, it works amazingly well, and you can stream to YouTube, which provides a free service which allows you to stream 1080p internet or video to your heart's desire over the internet. It requires about 5 megabits of traffic, so make sure you have enough bandwidth, but other than that, works really, really well. What I had to do to make this all work for my aquarium was I had to fix the ISO and gains and color correction amounts. Because otherwise, Raspberry Vid likes to auto color correct and such, and it'll start adjusting colors, and it will look all yellowy because it doesn't expect the colors to be underwater in an LED environment. So by fixing all the ISO, gains and such, I now have beautiful 1080p video that I can turn on when the lights come on and turn off when the lights go off. So far all we've talked about is connecting hardware to sensors, and that's about it. How do I actually get it to a dashboard? And this is where the IoT aspects come in. Many people have been doing those sensor connections for decades. There's nothing too new about that except for the cost point. What's really cool about IoT is the fact that my Raspberry Pi has an IP address, and I can get this information off of the device into a wide variety of different applications, whether it be a mobile device, a web page, you name it, machine to machine. This is where IoT comes in. And one of the great ways of doing this is using a messaging format called MQTT. There are many, many IoT messaging formats, and we're not going to get into all of them. But MQTT is a very lightweight one that works perfectly for this particular use case, which is I'm sending a message about once every 10 seconds, which for my application, perfect. IBM originally wrote MQTT. They open sourced it, and they created even some JavaScript implementations called Paho. Paho is a JavaScript implementation of an MQTT client, and I was able to take their Paho client and wrapper it and put it into this Freeboard dashboard to allow me to receive messages and use that information to make pretty graphs. So I'll show that later in the demo to be able to show how you can take information and portray it. But highly recommend MQTT for a wide variety of use cases. But again, many, many, many ways of doing this. You could use SOAP, you could use XML, you could use SCADA, you could use all sorts of different ways of doing messaging. IBM also provides, through their Bluemix platform, what they call IBM Watson IoT, or it used to be called the IBM IoT Foundation. This is an MQTT-based messaging format where they have implemented it. They provide all the back-end servers, so you don't have to worry about running an MQTT messaging server. All you have to do is to say, hey, I've registered my device, and you just put in your MAC address of your Raspberry Pi. And from there, you can start sending messages. And if you're interested, CloudOne does private implementations with custom deployments for large scale, and that's the end of my pitch. But that is effectively how a lot of IoT use cases can be solved, is using this MQTT type messaging format. So here's some very basic sample code for how to send an IoT message using the IBM Watson framework. What you're going to do is you're going to provide some configuration details, usually your device name and your secret, to connect to the IoT Foundation. Once you import in their library, the next thing you're going to do is you're going to also import in a JSON library, because it's nice to be able to JSON encapsulate your message if you're going to be using this on the web or for a variety of other purposes. That way you can easily parse out your message. So in my case, I just made a very simple example here where I said x equals 1, 2, 3, 4, 5, an integer. And I also have another thing in my data called string hello with value world. So I'm sending that as a JSON encapsulated message over the IoT Foundation. And it publishes that data, and anything else listening on that IoT Foundation for that particular channel will see that message. And it could be one device listening, or it could be billions of mobile applications around the world. I believe for a long time, and it may be still true today, Facebook messaging was built on MQTT. I'm pretty sure Uber still uses MQTT for a number of their car synchronization. So when you're watching the car show up to your door and you're wondering, how did they get like the exact GPS coordinates of where that car is and put it to my phone so quickly? MQTT. At least it was for a while. It may have changed. But very cool what you can do with this. It's very lightweight, very powerful, and a great way of sending messages. Then I could go into a lot more details of what you could do with MQTT, but that's enough for now. One of the other things that IBM puts out, and they open source this as well, it's called Node-RED. This is a Node.js implementation. Raise of hands, anyone used Node.js before? Anyone used Node-RED before? All right. All right, cool. If you've not seen Node-RED before, you don't have to know Node.js, but Node-RED is pretty cool. It's a lot of fun, and I'll show it here in the demo in a second. In fact, you know what? Forget that. Let's show it now. So this is Node-RED. What it is a framework of different actions, I guess I'll call it. I'm probably nodes, as they call it. And from that, you can visually create a program. So you don't have to be deep in programming knowledge to know how to use this, but it's very powerful. This is my state diagram of my aquarium, and it's grown significantly over time. But what you can see is I've got my aquarium event, and that is an instance of the IBM IoT Watson service. From here, I can quickly just dump it out to a message payload. And so within a few seconds here, one of the messages will come through, about every 10 seconds. Boom, there's a message. Now, I've done a very poor man's approach to this. There are better ways of doing this, but I literally just take all my variables, shove it into a message, and shoot it on out to the internet. It's IBM's problem to deal with now. There are probably much better ways of dealing with that, like, hey, what's an event versus what's a message versus what is status? And no, I've just shoved it all in there. There are better ways of doing it. But what you see happening here is every time an event comes through, it actually highlights this line. I don't know if you can see it. It'll show where it's going, and it makes it really cool to be able to do quick conditional logic. Like, for example, I want to take my flow information. So I'm going to say my property, take my message, and parse out from the JSON, from the payload, my water underscore flow variable. And if that number, which is an integer, is less than 2,000, send it to output 1. And if it's greater than 8,333, send it to output 2. And just looking at this, I say take each of those and drop that into a message construction where I say critical. The water flow is payload water flow. as measured on that particular date time of that. And from there, I can route that to a rate limiting to say, don't spam me with a ton of messages, only send me one per every 5 minutes, or 0.2 messages per minute, which is equal to 5. And then send me a text message. That's my phone number. Probably shouldn't put that on YouTube, but okay. Perfect. So this now allows me to receive notifications. So I've solved my primary use case. I want to now know, for example, the water level. When do I exceed 29 centimeters? That is the one number that I need to make sure I do not exceed 29 centimeters, because at 29 centimeters, when it gets to about 32, it's game over for my basement. So as long as I stay below 29, I have a reasonable amount of time to go and hopefully save the day. And it has actually saved me once or twice, mostly due to my own fault, because I didn't have the error checking on. But it works. I solved my primary use case through this messaging, and what I find great about this Node.js is how visual it is. I could easily have implemented this all in Python. That's obvious. But what's cool about it is the visual aspect to it. I don't know if I would necessarily use it in a production setting, but when you're tinkering around and changing a lot of variables and you're not quite sure where your project's going to go, this is a great visual way, if you're a visual learner, of seeing what your program execution should be, and then you could potentially map it into any language you want. All right. That pretty much covers this slide. There are so many different nodes that you can integrate to this. I don't know if you picked it up. One of the nodes I'm using is CloudOne, which is a cloud-based database. So one of the things I'll be talking about later is data analytics, because big data and aquariums they go together so well. We'll talk about that in a bit. And to kind of wrap things up, this project's been an evolution. It started out literally in a cardboard box. It's now got its own touch-sensitive screen with a nice project box. Most of the stuff I bought on Amazon Prime, which I'm a total addict, but all the pumps came from Amazon Prime. The water solenoid to turn off the water came from Amazon Prime. And Adafruit, shout out to them too, and Atlas Scientific. Between those three sources, that's where the vast majority of the equipment came from. And that's how it's all connected together. Again, it's totally stupid. Don't do this. So the next step for me is analytics. I did not cover the IR sensor, which is probably the coolest thing about this. In addition to my normal camera, I picked up another $25 infrared camera. All they do is most cameras that you buy have an infrared filter in front of it. They took the filter away, so it's just raw data. And what you can do with that is you can put another filter on top of your IR camera with a blue gel. And what that does is it knocks out all the blue spectrum from the light. So all you're left with is near infrared. Turns out plants do a lot of cool things in the infrared spectrum, but we as humans can't see it. But our IoT equipment can. So what it does is, this is actually my aquarium, and it looks like it's all dead, but in reality, when the infrared spectrum, it's all alive. And you can actually measure how alive are my plants in the infrared spectrum. If you've not seen infogram.org, it's really incredible what you can do. I'm sure in Indiana, especially, there's lots of farms around here. A lot of times farmers are actually sending up drones with this type of technology to measure their field's NDVI score, to be able to see how alive are different fields. And you can see all sorts of interesting information about different dosing of chemicals and fertilizers and the actual response of the plants. So now I'm not just controlling my equipment or just measuring it. In theory, I could start doing a linear regression model of the different dosing patterns to say, well, if I adjust the amount of phosphates or nitrates or potassium that I'm putting into my aquarium, what is the limiting reagent? How do my plants respond? How does the photosynthesis score start to get adjusted as a result of that? Now, I'm not quite there yet, but if this project's going to go anywhere, that's one potential place it could go. And of course, next steps here, you. This presentation is not about trying to make you go reproduce this exact setup, nor is it about working directly with this code. But I hope through this you've learned it's not that difficult. If I can do it, I'm confident just about anyone in this room can go and solve these type of things, and I would love to help for that matter. If you have any questions, feel free to reach out to me. I've got my GitHub address here where you can see my very, very bad code. I would not recommend using it, but if you want it as a reference point, please go take a look at it. And if you think this stuff is fun, please reach out to me. We've got a number of other people from CloudOne here, Jason Horn. We're building out a great team of people that are doing software development projects for IoT. We're looking to hire developers, data scientists, and we're helping build the future of IoT. So we'd love to talk to you if you find this fun. All right. Any questions? Yes.
So the one thing you said a few times you wouldn't use something in production, and I think you're selling yourself short because if I was getting water in my basement, I would not consider that a QA environment.
Yeah.
So a question not about the technology.
Sure.
How often do you get a message on your phone?
Oh, great question. During the early days, very frequently. The question was, so everybody hears, how often am I getting alerts to my phone? I was getting so many false positives that drove my wife nuts. She's like, you could practically flood the basement. She'd care less about that. What it took to get to more reliability, for a while I couldn't even debug why it was happening. It turned out for a long time I was using an insufficient power supply. Highly recommend getting a UL-rated power supply, not some cheap knockoff that doesn't come with a UL rating. Save yourself the hassle, get good power in, you'll have good results out. That would have saved me months of headache if I had that power supply. The other issue I had was with the water sensor. It took me a long time to get that calibration. I thought for a while, I'll take as many data points as I can and I'll really fit that line, and then my power was causing me issues, and it turns out I was using a voltage divider when in fact I should have been just using the straight out white pin to measure the voltage. So it took quite a few months. Today, as of like the last week, I maybe get about 2 or 3 messages a week, and they're all accurate. They're all correct. That's been a long road, though. The main messages I'm getting today are things like these maintenance things. Right now, daily I'm getting a CO2 reminder to say that my CO2 canister is low and I need to go replace that. And I'm coming up also on my 60-day notice for my filter. So these are now useful messages, but it took a while to get to that point. Great question. Any other questions? Yes, in the back.
Yeah, how reliable is the Pi hardware? Is this something like you plugged it in 3 years ago and it's good, or have you burned through a couple?
So how reliable is the Raspberry Pi? Up until I figured out that the voltage supply is so important, I thought it was a terrible piece of junk and I was about ready to throw it out. And it wasn't until I plugged in my touch screen and I started looking at a very special icon in the upper right-hand corner. If your voltage on your Raspberry Pi drops below a critical threshold, and the way they measure it is your USB port, if it sees the 5-volt line, I think, drop below like 4 volts or something like that, they will put a nice little cute little rainbow square in the upper right-hand corner of your display. And you'll be like, what the heck is that? I don't know why you're telling me there's a little rainbow square in my upper right-hand corner. And I Googled it one day, and it's like, your Raspberry Pi voltage is low, dude. You got to go get a better power supply. Well, that's nice. You could have put that in the log somewhere or something. Once I fixed that issue, it became highly reliable. I do use other embedded devices, though. Like I've used the TI Launchpad and the Arduino. They have nice perks. Lower voltage, a lot easier to control because you're not running a full Linux OS, and you get analog to digital converters, in most cases, built into the actual device. So the nice thing about the Raspberry Pi is learning curve very low and capabilities pretty high, and cost point very approachable. But there are other, sometimes better tools for the job. Good question. Yes?
On a short time scale, it seems like a lot of the things you're tracking with your sensors are probably pretty unpredictable. So I was wondering if you considered using your aquarium as a source of entropy.
So the question was, could I use this as a random function generator? Absolutely, especially on that water level sensor. Some of those measurements, and I'm still racking my head as I probably am doing something wrong. For a while, I didn't realize I was running 2 measurement things simultaneously. And if you're bit banging against an MCP and one thing is banging one way and the other is banging the other way, you will get really crazy results out of it. But at this point, I've got pretty reliable data, but even still, it's totally sometimes random. Luckily, with some good software filtering, I made it better. It does bring up an interesting discussion, though, about hardware-based controls for IoT. One of the things I've learned in this project that if I was really doing this for real is I really ought to have some hardware fallbacks to say, look, if some leak detector circuit sees that there's water on the ground, stop everything. Like, I don't care what your other sensors are saying, like something's seriously going wrong. And it brings about like whole discussion points of like, what should be part of, control signals of, should I allow anyone to go and do a water change remotely? How do I make sure that nobody does that poorly? But yeah, difficult to control. Yes?
So what's the grand total of the cost of this addition?
Best not to ask. What is the grand total of the... Yeah, thanks. You're really going to put me in the doghouse now.
Is there anything your wife's okay with this investment? It's because it was her thing to begin with?
So my wife is a data scientist, so I luckily have that working in my favor. What she hasn't allowed me to do is scale this problem, because clearly I need a sample size of 30 to make any accurate prediction, which she should agree with. No, to get to the actual cost, I probably spent about $1,000 on the minimum equipment for all the sensors involved. If I had $400, I could make a pretty good approach at this, and even if I had $100, I would have been able to solve my root case, which was control the water top-offs to a certain extent. I probably wouldn't have the level sensor, but I'd at least be able to put it on a timer and say after 30 minutes, cut that thing off because it's going to overflow, more than likely. So you don't have to spend $1,000 to go do this. For me personally, it's a rewarding hobby. Other people have cars, other people have musical instruments. This particular one is computers and high voltage and gas canisters and other things that could cost me a lot more in insurance. But yeah. Yes?
Not so much a question, but you said that you've been doing Python for a long time poorly. One suggestion is to quit using 8 spaces, and we'll like you a lot more.
Fair enough, fair enough. Yeah, I've been using Python off and on is basically the best way of putting it. I use it as a tool, not necessarily an art. So my code is quite poor, and it's in dire need of some refactoring for sure. But yeah, I probably should stop using the tab key and replace that with 4 white spaces. That'd probably be a good place to start. Maybe.
Any other questions for Ben? Let's all give Ben a round of applause.
Thank you.
Thank you very much.